Good morning to everyone. I am Dr.T.Ravi, Associate Professor and Head Department of Electronics and Communication Engineering, Sadhibama Institute of Science and Technology. So today we are going to discuss the topic subsystem design and ASIC construction. It comes under the course CMOS VLSI design. First, we are going to see what is meant by subsystem, because if you are going to develop any system, internally we are having some internal blocks. That blocks are called as subsystem. So now this session we are going to see how can we design the subsystem for the particular main system. So that is called as subsystem design. Suppose, for example, if you are taking any system, that subsystems, it may be like adders, multipliers, registers, like shifters or registers, then memory, then any PLDs like programmable logic devices. So these are the major subsystems for the main system. So we are going to start with basic adder. So the basic adder is nothing but half adder. Suppose if you want to add two binary bits, A and B, two binary bits we want to add, we are going to move for half adder. So the half adder, it will produce the outputs sum and carry. Sum is nothing but A XOR B and carry is nothing but A and B. Suppose if you want to add three binary bits instead of two binary bits, if you want to add three binary bits, we are going to use full adder. So here the inputs are A, B and C in, and sum and carry are the outputs. Sum is equal to A XOR B XOR C and carry is equal to AB plus BC plus CA. So we are very familiar in this. So here we are using two terms like generate and propagate. Generate is nothing but AB and propagate is nothing but A XOR B. So these full adders can be designed by using static CMOS logic, because in the previous topics we have studied about the static CMOS logic design and dynamic CMOS logic design. So these full adder can be designed by using the static CMOS logic. So here we are going to use the static CMOS logic. In this case, we are going to use PMOS and NMOS transistors. So in the pull-up network, we are using the PMOS transistor, and the pull-down network, we are using the NMOS transistor. So like this, we are developing the complete full adder circuit by using the PMOS and NMOS transistors. In the case of static CMOS logic, we need 28 transistors to complete the design. So here the sum is generating, or sum is estimating from the carry circuit. So here sum S is nothing but a final sum and CO is nothing but a final C output. So from the carry we are estimating the sum. So this design has been considered for 28 transistors. Similarly, the same full adder circuit can be designed by using the NP CMOS logic. So in the case of dynamic CMOS logic, either we can go for pure dynamic CMOS logic or domino logic or NP CMOS logic. From these, the NP CMOS logic is more efficient in the case of cascading of the circuits. Okay, fine. So here NP CMOS logic is nothing but phi n block, then followed by cascading by phi p block. So this logic is called as NP CMOS logic. So the adder can be designed by using the NP CMOS logic. Next, we are going to move for ripple carry adder. Suppose if you want to add two 4-bit data, that means A equal to 4 bits and B equal to 4 bits. So if you want to add two 4-bit data, this A and B. So for that case, we are going to move for ripple carry adder. So the ripple carry adder is nothing but, here we are going to cascading the full adders. Okay, so 4-bit data if you want to add means we are going to cascading 4 full adders, and the first full adder we are giving that input is A0 and B0 and external carry input, that is Cin. So it will be producing this output is sum S0 and C0. Then the second full adder is A1 B1 and the previous carry it's going to take as a Cin value and it will be producing the sum and carry value. So like this, the LSB bit to MSB bit, we are going to give the inputs to the full adder, and the carry is going to propagate from one stage to next stage. From input to output path. So this is called as 4-bit ripple carry adder. So if you want to add two 4-bit data, we are going to use we are going to use 4-bit ripple carry adder. Suppose if you want to add 8-bit data, suppose A is equal to 8 bits and B is also 8 bits. Suppose if you want to add two 8-bit data, we can go for n-bit ripple carry adder circuit. So for this case, n-bit ripple carry adder means, suppose for example nowadays we are using the processors or 32-bit processor or 64-bit processor. 64-bit processor, internal adder should be performed 64-bit data. That means A is equal to 64-bit, B is also is equal to 64-bit. Suppose both the data are 64-bit. So for that case, if you are going to use this ripple carrier adder concept, we have to add 64 full adders. We have to connect it in cascading process. We have to connect it in cascade. So for that case, after computing the first carry, the second full adder is going to compute the sum and carry value. After computing the second full adder, the third full adder is going to compute the sum and carry value. That means the carry is going to propagate from stage by stage from input to final output. So for example, you can take the one full adder generating time is 1 nanosecond time period. You have to assume that 64 full adders we are cascading means 64 nanoseconds time it's taking to give the final carry out. So this is, nowadays processors are very faster processor. So we have to make, or we have to find out the another method. That means we have to reduce the propagation delay of the carry path. So for that case, we are going to move for fast adders. In the case of fast adders, we are having different types: carry bypass adder, carry select adder, carry skip adder, and carry lookalike adder, and carry Manchester carry chain adder, and etc. We are going to see some of the fast adders in this. First, we are going to see the carry bypass adder. So here we are going to calculate the propagate value. Already we have discussed propagate is nothing but A XOR B. So for every full adder, we are giving A0 to A0 B0, then A1 B1, A2 B2, like this we are giving the value. So that by using that value, we are calculating the propagate value. So we are calculating all the propagate value P0 to P3. So here we are using one multiplexer, and all the propagate value we are giving to the one OR gate. The one AND gate, that AND gate value is given to the select bit of that multiplexer. That means, suppose for example, A0 and B0, these two values are 0, 1 or 1, 0. So for that combination, propagate is producing through the XOR gate. So in the case of XOR gate, different combination of the input will produce the output will become 1. So that case, the output is 1, then the Cin value is 1, means definitely we will get the carry value. So the Cin value, if all the propagate values are 1, so for that situation, the Cin value is directly bypassed to the second stage of ripple carrier adder. We no need to wait to come. We no need to wait for the conventional method of computing the carry value. So this is called as carry bypass adder. Based on the propagate value, if all the propagate values are 1, then the Cin value is directly bypassed to the second stage. If any one of the propagate values is 0, so for that time the carry is going to compute by the conventional way or normal way. It cannot bypass to the second stage. If all the propagate values are 1, then Cin value is directly bypassed to the second stage. So this adder is called as carry bypass adder. The next adder is nothing but carry select adder. Suppose if you are going to design 8-bit carry select adder, so we have to use 3 4-bit ripple carry adder. So here you have to see the structure. We are using 3 4-bit ripple carry adders. So this is the lower 4 bits, and these 2 ripple carry adder we are using for higher 4 bits. That means A0 to A3 and B0 to B3 and Cin value, these values we are giving this 4-bit ripple carry adder. And A4 to A7 and B4 to B7, the same values we are giving for these 2 ripple carry adder, and here we are giving the Cin value is equal to 0, and here the Cin value is equal to 1. Fine. So this ripple carrier, all these inputs are giving to the ripple carrier simultaneously. All these 3 ripple carriers are executing simultaneously. So for that case, this sum value, this sum value, this sum value, and these sum values are producing, and carry values are producing at a time. That means all the 3 ripple carriers are giving that outputs at a time. Then we have to see here this C4 value. If it is 0, these ripple carrier outputs are correct output. If this value is 1, then these ripple carrier outputs are correct output. So based on this carry value, we are going to select either these ripple carrier outputs or these ripple carrier outputs as a final output through the mux. Therefore, it is called as carry select adder. Based on this carry value, these outputs are going to get selected. Therefore, it is called as carry select adder. So you can get one doubt. So here we are using, instead of 2 full adders, 8-bit addition means we need 8-bit. 8-bit ripple carrier is enough. But here we are using 3 ripple carrier adder. But Here in the case of VLSI, if you are going to concentrate for speed, power and area, there is a trade-off between area and power and area and speed. Okay, so the area can get increased, but because we are concentrating only for the speed of computation. Okay, so here the total propagation delay, if you are going for conventional method, we have to cascading 8 full adder. So the total propagation delay from C in value to C out value. So here the total propagation delay is the propagation delay of the lower 4-bit triple carry adder plus the propagation delay of 1 mux. So this is the detailed circuit. So the propagation delay of the mux is very much less as compared to 1 full adder circuit. Therefore, it is very much equal to, or it is very closer to 1 4-bit triple carry adder propagation delay. Therefore, the total computation time is getting reduced because of this method. So in the case of carry select adder, based on this carry value, these outputs are going to get selected. Therefore, this adder is called as carry select adder. Okay, so the total propagation delay is the propagation delay of 1 triple carry adder plus the propagation delay of 1 mux circuit. Therefore, the total propagation delay is going to get reduced. That means the computation time is getting reduced, the computation speed is getting increased. So next we are going to move for multiplier. So nowadays we are, in conventional way, we are multiplying the two numbers. Suppose for example, you can take 2 4-bit numbers like S equal to 1101, B is equal to 1001. So these two numbers we are going to multiply. So 2 4-bit data we are going to multiply. Then finally we are getting the product output, final output is 8-bit value. So how we are making the multiplication? Conventional method. So for example here, X is nothing but multiplicand and Y is nothing but a multiplier. So conventional way of multiplication, we are taking this X naught, it is going to multiply with all the value of Y naught, Y. That means the multiplicand value X naught is going to take and it is going to multiply with all the value of Y. That means X naught into Y naught, then X naught into Y1, then X naught into Y2, X naught into Y3. So like this, we are making all the multiplication. Then we are taking for the next multiplicand, that is X1. This X1 is going to multiply with all the multiplier values. So that is the second row. So here this is the second position. Therefore, we are going to make the data with the second position to left. So like this, we are going to multiply all the multiplicand value with the multiplier. So we are getting this table. Then after making the multiplication, normally we are doing addition. So this value we are directly taking the first bit. Then these 2 bits we are going to add and we are giving as a second bit, and these 3 bits we have to add and we have to make the third bit. So like this, we are making addition for all these columns and we are producing the final output. So this is the process of array multiplier. So how can we develop the architecture for this array multiplier, or how can we develop the architecture for this functionality? So here first we are making the multiplication. So that multiplication process we can make through the AND gate, and this addition we can make through the adders. Okay, so if you are going to add 2 bits, we can use half adder. If you are going to add 3 bits, we have to go for full adder. So like this, we have to develop the architecture for array multiplier. So this is the architecture for array multiplier. So here the multiplication we are going to perform with this AND gates. Then the addition, after the multiplication, that addition we are going to make 2 bits means we are going to make by using half adder. Then this carry is going to give into the next stage. Therefore, here we are making through the full adder, and this carry and the another sequence is going to adding by using half adder. Only 2 inputs means we have to use half adder. 3 inputs means we have to go for full adder. So like this, we have to develop the complete architecture with respect to the complete functionality of this array multiplier. So this is the architecture for array multiplier, or this is the conventional, it is also called as conventional multiplier. Similarly, we can develop the Pauli multiplier and Booth multiplier. Pauli multiplier, it is like an array multiplier structure. That means it is a structure based multiplier. But the Booth multiplier, it is developed by the Booth algorithm. In the case of Booth algorithm, it can be shift and adding process is mainly taking as the concept. So for that situation, the Booth multiplier is developed by using the Booth algorithm. Fine. Next, we are going to move for shifter or shift registers. Shift register is a sequential circuit. It is a cascading of D flip-flops. Okay, and we are giving the synchronized clock signal to all the D flip-flops. So here the main component for this shift register is a D flip-flop. We know that the D flip-flop is nothing but delay flip-flop, and here we are giving the input to the D in, and we are getting the output from the Q, and we are giving the clock signal to the D flip-flop. We are giving the clock signal. So in the case of D flip-flop, we are giving D input and the clock input, and output is Q. Okay, so the D flip-flop is nothing but it is a single bit storage element, and also it will be producing the input value as the output value after some time delay. By using the D flip-flop, we can design the shift registers. There are 4 types of shift register: serial in, serial out shift register, serial in, parallel out shift register, parallel in, parallel out shift register, and parallel in, serial out shift register. So these are the basic 4 types of shift registers, and these are the corresponding functionality of these 4 types of shift registers. So this is the detailed structure or detailed structure of these 4 types of shift register. So in the case of serial in, serial out shift register, the data input we are giving in serial manner, and the data is going to propagate also in serial manner, and we are getting the data output in the final flip-flop output. So here we are giving a synchronized clock signal for all these shift registers, because the shift registers are, I mean all these flip-flop, the shift registers are the synchronized sequential circuit. Similarly, the serial in, parallel out shift register, the data is given in serial manner, and we are taken the outputs are in parallel manner. Therefore, it is called a serial in, parallel out shift register. Similarly, for parallel in, parallel out shift register, we are loading the data parallelly, and we are taking the outputs also in parallelly. Therefore, it is called as parallel in, parallel out shift register. Similarly, for parallel in, serial out shift register, the data loading to the shift register in parallelly, then the data is going to shifting from left to right in the case of serial manner. Therefore, it is called as parallel in, serial out shift register. So these are the 4 basic types of shift register. So these shift registers can shift the data 1 bit at a time with respect to each clock cycle. That means for every clock pulse, the shift register can shift only 1 bit data. Suppose if you, and also these shift registers are unidirectional shift register. That means it can shift only from left to right direction. It cannot be shifted by, both the direction. This is the unidirectional shift register. These basic 4 types of shift registers are unidirectional shift register. So to overcome this, suppose if you want to design bidirectional shift register, that means the data want to shift from left to right as well as right to left, we can go for bidirectional shift register. So in the case of bidirectional shift register, we can shift the data from left to right or right to left, but we cannot load the data parallelly. So for that case, we can go for universal shift register. In the name itself, it is defined that this is the universal. Universal means it can perform serial manner, or it can perform parallel manner, and it can perform left to right direction shifting or right to left direction shifting. That means the universal shift register can perform serial as well as parallel process, as well as the left. It can shift. It can shift from right to left or left to right. That means bidirectional shift it can process. So that's why it is called as universal shift register. So in the case of universal shift register, are designed by using D flip-flop and 4-to-1 multiplexer. So here, if the multiplexer, based on this select line of this multiplexer, that is S0 and S1, the functionality of this universal shift register is going to get decided. So if it is 0-0, there is no change. That means if it is 0-0 means this 0th bit value is coming to the D flip-flop. So this D flip-flop value is, this D in value is coming as an output, and this value again it is coming to the D flip-flop. Therefore, the same value will be continuously maintained in the circuit. So that's why there is no change in the output. That is called as 0-0 mode. If you are giving for 0-1, this universal shift register will perform shift right operation. Suppose for example, I am giving 0-1. 0-1 means that is the first one. First one, serial input for shift right. That means we are making the shift from left to right. Okay, so this value will be coming as an output, and this D flip-flop value is coming to the second stage of flip-flop. Second stage of mux. Then this mux value is coming to this flip-flop. This flip-flop value is coming to this mux. Therefore, the data is going to shift from left to right direction when the select bits are 0-1. Then the select bits S0, S1 is 1-0. So for that condition, 1-0 means this two, the pin 2 of the multiplexer is getting enabled. Therefore, this value, this input value is feeding to this D flip-flop, and this D flip-flop value is coming to this next stage of multiplexer, second bit. So this value is coming to this D flip-flop. Therefore, this data is going to rotate, shifting from right to left. Then 1-1 mode of operation, if I'm giving 1-1 in this select bit, so for that condition, this all 4 parallel bit input values are giving to the flip-flop. That means we are parallelly loading the data to the flip-flop. Therefore, in the case of universal shift register, it can perform parallel loading and it can perform left to right shifting or right to left shifting. Okay, so if you are going to make at the time of doing the left shifting process, that means it is going to multiply by 2 the value. Suppose, for example, the present value is 1-1. I'm going to make the left shift. So I'm going to make the left shift means these 2 bits are going to shift at this side. So this empty space is going to fill with 0. Therefore, I'm getting the values 110. So this value is equal to 6. So the previous value is 11. So the present value is 110. So this value is equal to 6. Therefore, this output value is going to, this value is going to multiply by 2. That means at the time of performing the left shifting, the value is going to multiply by 2. If you are going to performing the value to right shift, that time the value is going to divide by 2. Okay, fine. So this is the way the universal shift register is performing, shift right or shift left or parallel loading. Next, we are going to move for barrel shifter. What is meant by barrel shifter? So already we have discussed about the basic shift register, then we have discussed the universal shift register. Because in the case of universal shift register, it can perform left to right direction shifting or right to left direction shifting, or it can parallel loading also it can perform, but it can shift or rotate the data only 1 bit at a time with respect to the clock signal. Fine. Suppose if I want to shift the data more than 1 bit at a time, I have to go for barrel shifter. Fine. So in the case of barrel shifter, more than 1 bit I can shift at a time. So here we can use a combinational circuits to design the barrel shifter. Okay. So here you have to see the logical right shift by 2. That means if I want to make 2-bit right shifting means I can easily make with the hardware connections from these 2 bits are connected to these 2 bits. So like this I can make through the wire. So the design of the hardware is very cheap in the case of barrel shifter. Okay, and also conditional operation also we can perform. That means conditional operation means here we are using the mux. So if the mux value s is equal to 0, so that time these 4-bit values is coming as an output, s is equal to 1, these 4-bit values is coming as an output. So here these values are directly coming, that is A to D is coming to this output. Suppose here 2 bits are shifting and the rest of the 2 bits are only, it's coming like this. So this is called as conditional operation, shift versus no shift. Okay, so the barrel shifter can perform shifting more than 1 bit at a time. So this is the structure or this is the design for barrel shifter. So here X0 to X3 are the inputs and Y0 to Y3 are the outputs. Fine. So I'm going to make 0 shifting means there is no shift. That means X0 to X3 value should comes to Y0 to Y3 directly. There is no shifting. So for this case, I'm giving this value. You can assume these are the transistors. Okay. So this value is, if I'm giving a shift is equal to 0, these transistors are getting enabled. Therefore, this X0 value is directly coming through this transistor to Y0, and X1 value is directly coming. This transistor is getting activated. Therefore, this X1 value is directly coming to the Y1. Similarly, for X2 value is coming through this transistor to Y2. Through this transistor, X3 value is coming to Y3. That means there is no shifting. Directly, that X0 to X3 value is coming to Y0 to Y3. Suppose if I want to make 1-bit shifting. 1-bit shifting means I have to give the control signal to here. So this transistor is getting activated. Therefore, this X0 value is coming to Y1 through this transistor. Okay, so this transistor is getting activated. That means this diagonal up transistors, all these diagonal up transistors are getting activated. So the barrel shifter are designed, the control signal is passing through the diagonal up direction. Therefore, these transistors are getting activated. Therefore, this X0 value is coming to Y1, and this transistor is getting activated means this X1 value is coming to Y2 and this X2 value is coming to Y3. Similarly, this X3 value, this transistor is getting activated. Therefore, this X3 value is coming to Y0. Either we can shift the data or we can rotate the data either 1 bit. Similarly, if I want to shift 2 bit at a time, instead of 1 bit, I want to go for 2 bit shifting. So for that case, these transistors are getting activated. Therefore, this X0 value coming through this transistor to Y2, and this X1 value coming through this transistor to Y3. Therefore, X0 is coming to Y2 and X1 is coming to Y3. Similarly, this X2 is coming to Y0 and X3 is coming to Y1. So like this, we can make the 2-bit shifting. Similarly, we can go for 3-bit shifting also we can perform. 3-bit shifting means this X0 value is directly connected to Y3. Then similarly for this X1 value is coming to Y0 and the X2 value is coming to Y1 and the X3 value is coming to Y2. So like this, I mean through this diagonal it is connected. Therefore, this shift 3, these transistors and these diagonal transistors are getting activated. So through this shifter, barrel shifter, we can shift either 1 bit, 2 bit or any number of bits we can design. I mean we can shift based on that we are designing the architecture. So this design can be done by using only the basic MOS transistor. So here you have to see these are NMOS transistors. So if it is 1, then this transistor is getting on. If it is gate input is 0, this transistor does not getting on. Suppose for example, there is no shifting. That is S is equal to 0 condition. This diagonal transistors are getting activated through the control signal. Okay, so these are the control signal is passing through this, to this transistor. Therefore, these diagonal transistors are getting activated. Therefore, this transistor is getting activated means this A0 value passing through this transistor to D0. That means it is passing through this transistor and it reaching here, then it is going to this D0. Therefore, A0 is coming to D0. Similarly, A1 is coming to D1. Suppose if I am going to make for 1 bit shifting, I am giving the control signal values 1 here. Therefore, this transistor is getting activated. Therefore, this A1 value is passing through this transistor and it reaching to D0. That means A1 is coming to D0 and A2 is coming to D1 and A3 is coming to D2. That means here this transistor is getting activated, then this diagonal transistor. This transistor is getting activated means this A2 value is passing through this transistor to D1. Okay, so like this 1 bit shifting we can make. 2 bit shifting means this here we are giving this control input is, this gate input is 1. So for this condition, this signal, that means A2 signal passing through this transistor and it reaching to D0. So A2 is coming to D0, A3 is coming to D1, then A0 is coming to D2 and A1 is coming to D3. So like this, we can make this shifting either 1 bit shifting, 2 bit shifting, 3 bit shifting, like n number of shifting we can make. So for this case, the barrel shifter can be designed. The control signal is passing through the diagonal direction. So this is the shift 0, then this is the shift 1, this is the shift 2, and this is the shift 3. So like this, the diagonal transistors are connected the control signals. Okay, so this is nothing but a barrel shifter. So this is the 4x4 barrel shifter layout design. So here you can see the control signal SH0, it is passing through in diagonal way. Okay, similarly for SH1 is also passing through diagonal way, SH2 is also passing through diagonal way. So like the control signal is passing from lower to diagonal to the direction. So like this we can design for n cross n barrel shifter we can design. Okay, so we can make the shifting either 1 bit, 2 bit, any number of bits we can shift. So this is called as barrel shifter. Okay, so this is nothing but 4x4 barrel shifter layout design. Fine. So next we are going to move for PLD. PLD is nothing but programmable logic devices. So programmable logic devices are then PLA and PAL. What is meant by PLA and what is meant by PAL? PLA is nothing but programmable logic array. PAL is nothing but programmable array logic. So this PLA and PAL are nothing but programmable logic devices. So here both cases, that means both cases like PLA and PAL, it consists of 2 plan or 2 arrays, two plans like AND plan and OR plan. So in the case of PLA, both plan are programmable. That means AND array as well as OR array both are programmable. But in the case of PAL, the AND array is programmable, OR array is fixed one. So this is the main difference between the PLA and PAL. PLA is nothing but programmable logic array. So the programmable logic array, it consists of two plans, unplanned as well as R plan. Both plan are programmable. But in the case of PAL, in the case of PAL, both plan PAL unplanned is programmable and R plan is fixed one. Fine. So we are going to move So in the case of PLA and PAL, it consists of two plan, underplan as well as the R plan. We are giving the inputs to the underplan. We are taking the outputs from the R plan, and the lines are connected. And the lines are connected between unplanned to R plan is called as product lines. Okay, so the lines are connected between unplanned to R plan is called as product lines. We are giving the input to the unplanned. We are taking the output from the R plan. The lines are connected between unplanned to R plan is called as product lines. So here the total size of the PLA or PAL is going to define with respect to the number of inputs, number of outputs, and number of product functions or number of product lines. With respect to these three only, the total size of the PLA is going to decide. Okay, so here we are going to see one example for PLA design. So this is the detailed structure for underplan as well as the R plan. We are giving the input to the unplan and we are taking the output from the R plan. And the lines connected between unplan to R plan is called as product lines. So here, suppose if you are going to design a PLA for some particular function, so first we have to make the truth table for the particular combination logic. First we have to make the truth table. Then we have to find the SOP terms, sum of product function, by using either Boolean algebra or K-map. By using any K-map method, we have to find the sum of product function. That means we have to find out the Boolean expression. After that, how many variables we are using in that expression, that will be defining the number of inputs to the PLA, and how many product terms in that expression we are having, that will be deciding the number of product lines, and how many output variables we are getting, that will be deciding the number of output lines. Okay, so this is the way we are defining the designing the PLA. PAL, here the same process. First we are taking the combination circuit, we are making the Boolean function, then we are making the inputs with respect to number of input variables and number of product lines based on the number of product terms, and here the outputs are fixed one because the OR gates are fixed in the case of PAL. That is the only main difference between PLA and PAL. So now we are going to see one example. Design PLA for the given function y1 and y2. So here y1 is equal to AB plus BC, y2 is equal to A bar B plus BC. So now we are going to design the PLA for this given function y1 and y2 by using NOR logic, because the PLA can be designed by using NOR logic or NAND logic. So that underplan, already we have discussed, the PLA consists of two plan, one is underplan, other one is R plan. Okay, under array and R array. Both array, if you are going to design by using NOR logic, that is called NOR PLA or NOR PLA logic. If you are going to design both the plans by using NAND logic, that is called NAND logic PLA or NAND PLA. Okay. So first we are going to see, first we are going to design the given function by using NOR logic PLA. So for this, we are taking the function y1 is equal to AB plus BC. First, we have to convert the given function in terms of NOR function. For example, you can take the first function y1 is equal to AB plus BC. So here, AB is the multiplication function. We know that the NOR function means A plus B the whole bar. If you are getting like that, that is called as NOR function. So first we have to convert the given function in terms of NOR function. So for that, we are taking y1 is equal to AB plus BC. Then we are going to apply double bar. If you are applying double bar, the functionality does not going to get changed. So after that, we are going to apply the De Morgan's law. What is De Morgan's law? Do you remember? I hope. The De Morgan's law is nothing but we can break the line and change the sign. So that is the De Morgan's law. So here we are going to break this line and we are changing this sign. Here it is addition function. So we are going to change it as an multiplication, and at the time of we are breaking this line. So we are getting AB bar into BC bar, the whole bar. Again, we are applying the De Morgan's law for this AB bar. Okay, for this AB bar, we are applying De Morgan's law. So we are going to get A bar plus B bar. Similarly, for this we are going to get into B bar plus C bar the whole bar. Again, we have to apply the De Morgan's law. So we are going to get, we are breaking this line and we are changing this sign. A bar plus B bar the whole bar plus B bar plus C bar the whole bar. So now you have to see, you can take this as X, or P, and this as Q. So P plus Q P plus Q the whole bar means that is nothing but NOR function. Okay, so here we are going to make the NOR logic by using only NMOS inverter logic. We should not go for static CMOS logic. We are going to make only NMOS inverter logic, because in the case of only NMOS inverter logic only, we are having less number of transistors. So in the case of only NMOS inverter logic, here we are having the depletion mode transistor and the gate is connected to the output. Okay, and here we are giving the inputs. So the first input is A bar, I am giving here. The second input is B bar, I am giving here. So these two transistors are connected in parallel because it is a NOR operation. NOR operation means A bar plus B bar the whole bar. So it is nothing but NOR operation. We have to connect these two transistors in parallel and we are giving the inputs A bar and B bar here. So we are getting the output is A bar plus B bar the whole bar. So we got the first term. Fine. Similarly, we can go for the second term with the input of B bar. Other input is C bar. We can get the B bar plus C bar the whole bar. So like this, we have to make one more structure for this second term. So that finally we are getting these. This is the first output. Similarly, we are getting B bar plus C bar the whole bar. That is the second output. That two outputs we are going to give one more two input NOR gate as an input. So this output I am going to giving here, and another output I am going to giving to this transistor. Then finally I am going to get this expression. So this expression is nothing but Y1 bar, because here we are getting whole bar, but here there is no whole bar. Therefore this is nothing but Y1 bar. So if you are going to design the PLA by using NOR logic, finally we are getting Y1 bar as output. Then, but we have to get Y1. Am I right? The function is an Y1. So finally we are going to connect one inverter in the final output stage. We can get Y1. Okay. So this is the way we have to convert the given function to NOR logic first. Okay. So now you have to see here, the first term is AB. Am I right? The first term is AB. So if you are going to convert to NOR logic, we are getting the inputs are A bar and B bar. Okay. That means the inverting value or inverting variable we are getting as an input. AB as a given function, but we got A bar and B bar as an inputs. So the inverting variable only we are getting as an input in the case of NOR logic. So this is the detailed implementation structure for this Y1 and Y2 using NOR logic. So this function already we have discussed how we are converting the given function to NOR logic like that. So now you have to see here one depletion mode transistor, one end is connected to VDD, other end is connected to output. The same way, here I am making the depletion mode transistor, one end is connected to VDD, other end is connected to output. So this horizontal line is nothing but a output line for this AND array, not final output. This is an output for this AND array. So here I am giving that the inputs are for, okay, you have to see this variable. What are the different inputs variables we are having? A, B, C we are having. So three variables we have to use A, B, C. So this is A. If you are putting bubble, this is nothing but A bar. So A bar, B bar, C bar. So totally six vertical lines we have to make for three inputs. Okay. So these horizontal lines are represent the product lines. Product lines means how many product functions we are having here. So this is AB is one first product function. BC is another product function. A bar B is the third product function. So BC is the repeated function we should not consider. So the non-repeated functions only we have to consider. So totally three product functions we are having. Therefore, we have to make three horizontal lines. These horizontal lines are nothing but a product lines. This vertical green color, these six green, six lines are called as input lines. These final two lines are called as output lines. That means input and output parallelly we are making vertically, and horizontally we are making the product lines with respect to the product functions. So we are having three product functions, therefore we have to make three horizontal lines. Fine. So first case, the first depletion mode transistor is connected, one end is connected to output, VDD, other end is connected to output. So here the input is A bar, other input is B bar. So this is the line for A bar. So here I have to make the transistor. That means the gate is connected to this transistor. That means A bar input is connected to this transistor, and the one end of the transistor is connected to output, other end is connected to ground. So the same way we have to design, one end of this transistor is connected to this output line, the other end is connected to ground. So this is the input of the transistor A bar. Other transistor is input is B bar. So this is the B bar line. So here we have to make the transistor. Therefore, these two transistors are connected in parallel, and one end is connected to output line and other end is connected to ground. Okay, so the pull down network is completed. Similarly, the pull up network here we are making. Therefore, this three transistors represents the first implementation of two input NOR gate. Okay, these first three transistors. So this is the first output product line belongs to the function AB. Similarly, we have to make the transistors for the function BC and A bar B. For BC means we have to give the inputs for B bar and C bar line. That means the transistor we have to make in B bar line as well as the C bar line. Similarly, for A bar function, A bar B means we have to get the input is A, other transistors is B bar. So like this, we have to complete the AND plan side. Now we are going to move for OR plan side. In the case of OR plan also, we have to follow the NOR logic. So the depletion mode transistors we are making, one end is connected to output, and this vertical line is nothing but a final output. Therefore, this another end is connected to this way. So here, the first output is the Y1 function depends on AB and BC. So this is the line belongs to AB. This is the line belongs to BC. Therefore, here we are making transistors. That means this is one transistor, this is the another transistor, and this is the output line for Y1 bar, because we are getting only Y1 bar. Then finally we have to connect one inverter. Finally we are going to get Y1. Similarly, for Y2 function depends on A bar B and BC. This is the line belongs to BC, so I am making one transistor here. This is the line belongs to A bar B, therefore I am making another transistor here. Therefore, these two transistors are connected in parallel, and this is the depletion mode transistor. Therefore, these three transistors are nothing but this way of configuration. So I am getting Y2 bar here. Then finally I am connecting one inverter here. I am getting final output is Y2. Therefore, the inputs are ABC, output are Y1 and Y2. The number of product functions are 3. Therefore, we are having the 3 horizontal line. So this is the complete implementation of the given function Y1 and Y2 with by using the NOR logic or NOR logic. The same way, the given function can be designed by using NAND logic also. How can we design the NAND logic? First, as it is, we have to convert the given function in terms of NAND function. Y1 is equal to AB plus BC. This is the AND function. We have to convert it to NAND function. So we have to apply double bar, then we have to apply the De Morgan's law again. We are going to break the line and change the sign. So we are getting AB bar into BC bar, the whole bar. You can take this is P and this is Q. P into Q, the whole bar, that is PQ whole bar, that is an AND function. AB bar is one NAND function, BC bar is another NAND function, the whole term is another NAND function. So here also we are going to design by using the only NMOS inverter logic. So in the case of only NMOS inverter logic, in the pull-up network we are having only one transistor, that is a depletion mode transistor, gate is connected to output, and the pull-down network, the transistors will be connected in series, because in the case of NAND function, the function is a multiplication function. Therefore, the transistors will be connected in series. So these things we are already discussed in the previous topics. Okay, so here this is the way we have to make the structure. Okay, so here you have to see the first term AB. We are getting that input is also AB. So if you are giving input is A, another input is B, we are getting AB bar. So first term we got. So here direct variable we are giving as an inputs in the case of NAND logic. But in the case of NOR logic, the complement variable as an input. But here direct variable as an input in the case of NAND logic. Okay, so first we have to convert the given function to the NAND function. Then we are going to implement by using two input only NMOS inverter logic, two input NAND gate logic. So this is the detailed implementation diagram. So here you have to see first function. For this first case, input is A, other input is B. So this is the line A, and this is the line A bar, B, B bar, C, C bar. Similar way, 6 lines and 2 output lines, 3 horizontal lines. So here the first input is A, so I am making the transistor here. The second input is B, I am making the transistor here. So the transistors will be connected in series. Therefore, this end is connected to ground. One end is connected to ground, other end is connected to VDD. These two series transistor, one end is connected to ground, other end is connected to output. Therefore, here it is connected to ground, this terminal is connected to output. And here we are making the depletion mode transistor. So this 3 transistor configuration is nothing but 2 input NAND gate design. Similarly, we have to make for second function BC. So this is the input B. So here I am making the transistor. C, another input is C, so I'm making the transistor same input line. So this is the two transistors, then I'm making the depletion mode transistor here. So like this, the second term is completed. The third term is first input is A bar, second input is B. So I'm making the transistors in series, and this is the underplanned design for this given function by using NAND logic. Okay. The similar way we have to design in the OR plan side also. In the case of OR plan side, we have to use the same concept. The Y1 function depends on AB and BC. Y1 output function depends on this line AB and line BC. So here I am making one transistor, here I am making another transistor in serial manner, and this side I am connecting the ground, and here I am making the depletion mode transistor. So here I am getting the direct output Y1 directly from this circuit. Then Y2 function I'm getting directly from this circuit. So if you are going for NAND logic, directly I'm getting Y1 and Y2 as a final output. Okay, so the PLA can be designed by using NOR logic, or PLA can be designed by using NAND logic. So this is the corresponding stick diagram. So you are very familiar with the stick diagram design. So all vertical lines, all the input lines, we have to make the polysilicon red color, and all the horizontal lines we have to make by using the diffusion. So here we are making the diffusion, that is the P diffusion, that is the green color we are making. So here wherever we are having a transistor, that place just you don't put anything. These rest of the places we have to put the ion implants. If you are putting the ion implant, that means it is default, it is connected. But here, with respect to the value of A, that this particular transistor is going to get closed. The rest of the places, these places, the transistors, these are already closed. So with respect to A and with respect to B only, these two transistors are going to get closed. So wherever we are having the transistors, you don't put the ion implant. The rest of the place, you have to put the ion implant. And this side, we have to put the ground, and here we are making the depletion mode transistor, and this is the VDD line we are making here, and we are making the 3 depletion mode transistors. Okay, so like this we have to make the stick diagram for underplanned side. Similarly, we have to make the stick diagram for OR plan side. You have to see here, up to this the diffusion is coming, but from here to here we have to make by polysilicon, because this is the input for this OR plan. Am I right? So this is the input for this OR plan. So we have to make this input by using red color, that is the polysilicon. If it is in polysilicon, then these things we have to make by diffusion, then only it can be represented as a transistors. So wherever we are having the transistor, don't put ion implant. The rest of the places we have to put the ion implant. So here we are making the depletion mode transistor. Finally, we are getting Y1 and Y2. So this is the stick diagram for the given function using NAND logic PLA design. Fine. So the PLA can be designed by using two logics. One is NOR logic, other one is NAND logic. If you're going for NOR logic, first the given function should be converted to the NOR function, then we have to make the design. If you're going for NAND logic, the given function should be converted to the NAND function, then we have to make the design. Fine. Next, we are going to move for VLSI design flow. So in the case of VLSI design, we are having two major parts. One is ASIC, other one is FPGA. What is meant by ASIC and what is meant by FPGA? Suppose, for example, nowadays we are using the i7 processor. Suppose anyone is developing new processor. He's telling that this is my innovative processor. This will be performing very faster than i7 processor, like that he is telling. So for that situation, immediately the people does not going to make the fabrication. First, they are going to check in real time in hardware level. Then, if it is getting success, then they are going to make for final chip level design. So for that case, we are having two major branches. One is FPGA flow, other one is ASIC flow. First, we are going to see FPGA flow. In the case of FPGA flow, first we are having some design idea. So the design idea, we are going to make it as a programming structure by using the HDL, hardware description language. By using the hardware description language, we are making the RTL code for the particular concept. Then after making the RTL code, that means after our ideas is developed as a programming structure, we are going to make the simulation. Through the simulation, we can check the functionality. That means that the program has been developed as per the logic or not, like that we are checking through the simulation process. Then we are going to do the synthesis. So at the time of making the synthesis, we are converting the RTL code in terms of logic slices. That means in terms of lookup tables. That means all the flip-flops and sequence circuits is going to convert as an lookup tables, and all the combination circuits are going to convert as an logic slices. That is called as a synthesis process. Then after doing the synthesis process, we are going to make floor planning, placement and routing. Then finally, I will explain what is meant by floor planning, placement and routing later. So after doing all these process, finally we are generating the bit file. That bit file only we are going to download into the FPGA. After downloading into the FPGA, that means FPGA is nothing but it is a reprogrammable chip. Okay, we are going to download that bit file over that FPGA. So that time that FPGA it works for that particular architecture. Okay, it works as a chip for the particular architecture. So they are going to test in real time. Then if it is getting success, then they are going for fabrication side. So this is called as FPGA flow. Then other one is ASIC flow. ASIC is nothing but application specific integrated circuit. ASIC flow, basically ASIC it consists of two types. One is full custom ASIC, other one is semi-custom ASIC. What is meant by semi-custom ASIC? What is meant by full custom ASIC? In the case of suppose for example, you are developing the architecture. So the basic transistor alone, the basic transistor also, if you are developing that layout of the basic transistor, basic logic gates, everything you are developing by your own, and if you are by using your own logic cells, if you are developing the architecture, that is called full custom design. Semi-custom design means already the basic cells and basic logic gates are already developed, it is available in the library. We are going to use that developed basic cells and logic gates and we are developing the architecture, that is called semi-custom ASIC. In the case of full custom ASIC, first we have to develop the schematic, that is a CMOS design is nothing but a schematic design. Then we are going for simulation. After making the schematic, so already we have discussed like static CMOS logic design and dynamic CMOS logic design. So like this already we have discussed in the previous topics. So here the schematic is going to develop. Schematic can be developed by using any logic like static only NMOS inverter logic or static CMOS logic. Any logic we can use and we can develop the schematic. Then after making the schematic, we are going for simulation. So already I told simulation is used to check the functionality. That means logical functionality. The circuit has been designed as per the logic or not, like that we are going to check. That means we are giving some set of inputs and we are run the circuit and we are checking that output. That is nothing but a simulation. Then after that we are going to make the layout. So already we are making the schematic, then we are going to make the layout. So already you are familiar in the case of how to make the layouts. So with respect to the schematic, we are making the stick diagram. Then after the stick diagram, we are making the layout design. So after making the layout, we are going to do the DRC and LBS. What is DRC and LBS? DRC is nothing but design rule check. Design rule check means at the time of making the layout. So the main difference between stick diagram and layout, in the case of stick diagram, we are not maintaining any dimensions. Only the standard colors we are using, and we are making the layers we are going to represent. But in the case of layout design, we are going to represent the same layers by using the same color, but standard dimensions. With the standard dimensions we are making, that is called as a layout. Okay. So at the time of making layout, for example, the polysilicon means the width of the polysilicon should be 2 lambda. Width of the metal layer is 3 lambda, and the space between one layer to another layer should be 1 lambda. So these things are we are maintained or not, like that we can check through the DRC. That is the design rule checker. Then the next one is LBS. What is LBS? Layout versus schematic. What is mean by layout versus schematic? Because first I made the schematic, then I have I have simulated the schematic, I have checked my functionality is correct or not, like that. Then I am making the layout. So I have to check my layout is exactly made for that schematic or not. So for that case, I am going to do the LVS. It is going to match the both, match the layout as well as the schematic. So if it is getting matched, then the layout is perfectly designed with respect to the schematic. So that is the process we are doing for LVS. Then we are going for post-truth simulation. Then after that, rest of the process we are doing. Then finally we are making the GDS file, graphic design file. So GDS 2 or 3, 4, nowadays it's come up to 4. So this is the this is called as ASIC flow. Okay, so the VLSI design we are having FPGA flow as well as the ASIC flow. So now we are going to see one more concept in detail, that is a CMOS design. So that is nothing but, sorry. The case of ASIC flow, in that main part is physical design. So what is a physical design? Then what is a physical design flow, like that we are going to see. So here we are starting with the system specification. Then we are going to move for architectural design. System specification means, suppose for example, I'm having some idea in my mind, I want to develop an architecture. Okay, fine. I want to develop some particular concept. So that concept is going to called as system specification. Then my concept is going to develop as an architecture. So suppose I'm having some ideas, that idea I'm going to make it as an architectural level. So that is called as an architectural design. Then functional design and logical design. So my architecture is going to make it as an logical design or functional design, means it's going to make it as a programming or RTL code level. That is the by using HDL languages we are making the RTL code level. Then circuit design. Circuit design means we are going to convert the RTL code in terms of logic cells or logic slices. So that is called as a circuit design. Then we are going to move for CMOS design, that is a transistor level design, that is called as a physical design. So in the case of physical design, we are starting with transistor level design, that is a schematic, layout, the other process we are going to do. Okay, so in the case of physical design, we are doing some process like partitioning, floor planning, placement and routing. So these are the major 4 steps we are doing in the physical design. So after making schematic design, then we are going for layout design. Then after making the layout, we are going for partitioning. What is meant by partitioning? Suppose for example, if you are going to construct the house, okay, first we are going to decide what is the total size of the house. Then we are going to decide how many blocks or how many rooms we are going to keep in our house, like that we are deciding. So 2 bedrooms, 1 kitchen, 1 dining hall, 1 hall, like this we are decided. Okay, like that, this is called as partitioning. That means the total house area is going to partition as the different rooms. So this is called as partitioning process. So like that, if you are going to make the architecture, the total system is going to divide it into subsystem. So each subsystem we are going to define like the total system is going to divide it as 5 subsystems, like that. So that is called as partitioning process. Then after partitioning, after decided, we are making the construction. So that time we are exactly marking the area for this room and hall, every places, for everything. Then we are then after that we are constructing the building. So that marking every thing properly, that is called as floor planning. That is, floor planning means after decided or after dividing the total architecture into sub blocks, then we are going to decide where we are going to keep the blocks. Block 1 here. Suppose for example, you have decided 2 bedroom, 1 kitchen, 1 hall, like that. Then 1 dining hall. So in the south corner, I am decided kitchen room. Then north corner, I am going to keep the dining hall. Middle, I am having the hall. If you are keeping like this, it will be comfortable? No, because we have to keep the dining hall very closer to the kitchen. Then only we can shift the things easy, comfortably. So like that, what are the blocks are communicating frequently? That 2 blocks we have to keep very closer. Okay, so like that we are deciding the blocks where we are going to keep in the total chip area. So that is called as floor planning process. Then after deciding this, we are constructing the building. Okay, as per the final decision, we are constructing the building. The same way we are building the particular blocks in that specified area. So that is called as placement process. Then the next one is routing process. Routing process is nothing but, okay, our building is constructed completely. Then after that, we are making the path from our house to road. Okay, so that we are making the path, that is called as routing. Okay, the same way blocks are developed or blocks are constructed in that place, but the blocks has to be connected. That is called as routing. Okay, so here local routing and global routing. So we have to make for clock routing, then signal routing. The main important for clock routing, from the clock pin, the clock signal should be reached to all the nodes exactly the same time. Otherwise, we will face the clock skew problem. Am I right? So we have to suppose, for example, which block is very closer to the clock pin, it is getting the clock signal very quickly. Which block is somewhat away, it is getting the propagation delay of the clock signal, it will be taking little more time. So that block is receiving the clock signal after some time only. So that things we have to make common for all the blocks. That means the clock signal should be reached to common to all the blocks. That is called as clock routing. Then signal routing, that means suppose the first block is transmitting the data or receiving the data from first block to second block, so we are making the connection, so that is called as signal routing. So within the block, if you are making the connection, that is called local routing. One block to another block, if you are making the connection, that is called global routing. So these are the main process: partitioning, then floor planning, placement, then routing process. So these are the flow for physical design process. Okay, then after completing this, we are going for physical verification. That means we are making for DRC, LS, and etc. Then finally we are fabricating the IC. Okay, after fabrication we are making the testing. Then after testing we are making the packing of the chip. Then finally the chip has been released. Okay, so this is the complete ASIC flow. ASIC flow design. ASIC design flow, or this is the complete physical design flow. So this ASIC design flow can be simplified. We can represent synthesis, then timing analysis, that means simulation. Then we are going to move for floor planning, placement, and routing. Then finally we are manufacturing the chip. So that is called backend design. So if you are making RTL code and if you are doing simulation, synthesis, these processes are called as front-end process. Then starting from schematic, layout, then floor planning, placement, routing, and up to GDS2 conversion is called as backend design. So this is the simplified ASIC design flow. Thank you.